Every single atom in your body has a cosmic origin story written over billions of years. This video will decode the 15 critical turning points in cosmic history that determined the fate of everything from the first instant of time to the distant future. You will learn how a series of random cosmic events perfectly set the stage for your existence. We will explore how the universe emerged from a single point of infinite heat and density, and why a tiny imbalance between matter and antimatter means you are here at all. How did a uniform energy soup transform into the complex cosmos of galaxies and life? This journey reveals the ultimate origin story, connecting the universe's birth directly to you. What does it mean to be made from the ashes of long-dead stars? This first instant of existence remains the deepest mystery in all of science. We have no telescope powerful enough to peer into that initial flash, no equations robust enough to describe its chaotic, unified nature. The Planck epoch represents a true boundary of human knowledge, a wall beyond which our current understanding cannot pass. All we can do is trace the cosmic aftermath backward, like detectives reconstructing a crime scene from the scattered evidence left behind. The pivotal clue came when this single superforce could no longer hold itself together. Immediately after that first unimaginable moment, the universe began a frantic expansion, cooling just enough to trigger the first great divorce in cosmic history. Gravity, the force that would one day sculpt galaxies and hold planets in their orbits, broke away from the unified superforce. This was the universe's first step toward complexity, the moment the stage was set for everything that would follow. With gravity now operating on its own, the primordial cosmos was poised for its most spectacular transformation yet. This separation of gravity was just the beginning. The infant universe, still less than a trillionth of a second old, entered its next critical phase. Here, the remaining fundamental forces were locked in a unified embrace. The strong nuclear force which glues atomic nuclei together, and the electroweak force, a combination of the electromagnetic and weak forces, acted as one. This was the grand unification epoch, a fleeting era of unimaginable simplicity and power. For a sliver of time so brief it defies human comprehension, the cosmos was governed by a single set of rules. This was a seething ocean of pure energy, a place so turbulent that particles and their antimatter counterparts spontaneously burst into existence, only to annihilate each other an instant later in a continuous, furious dance. It was within this cosmic pressure cooker that the universe made choices with permanent consequences. The specific way in which these forces eventually split apart was not random. It set in stone the fundamental strengths of nature's interactions. It determined how strongly atomic nuclei would bind, and it laid the groundwork for the chemistry that would one day become the basis for life. The constants of nature were being forged in this primordial fire. The stage, having been set with these new rules, was now primed for the most violent and transformative growth spurt the cosmos would ever experience. All that unified energy needed an outlet, and it found one in the most spectacular growth spurt imaginable. The universe did not simply expand, it exploded in scale at a rate that defies all common sense. In a span of time so brief it makes a nanosecond feel long, the cosmos swelled from a size smaller than a single proton to a volume larger than everything we can currently observe. This was the inflationary epoch, a cosmic hyperdrive that solved some of the universe's deepest mysteries in one breathtaking moment. Why does the night sky look roughly the same in every direction, a concept called homogeneity? Why is the fabric of space itself so remarkably flat, meaning parallel lines never meet? Inflation answered these questions by stretching the primordial cosmos so incredibly fast and so incredibly far that any initial lumps or curvatures were smoothed into the uniform, flat sheet we detect today. But this process was not perfectly smooth. On the tiniest quantum scales, tiny fluctuations were inevitable. Think of the surface of a rapidly inflating balloon. From a distance it looks perfectly smooth, but up close you would see the minute textures and wrinkles in the rubber. Inflation did the same thing to spacetime. It stretched those subatomic wrinkles, those quantum jitters, to astronomical proportions. These stretched ripples became the gravitational seeds for all future structure. Every single galaxy, every star, every planet you see traces its origin back to those microscopic imperfections. This explosive growth also acted as a cosmic reset button. It diluted any exotic, leftover particles from the earlier, more chaotic epochs, wiping the slate clean and creating a fresh, hot, and uniform canvas. When this frantic inflation finally ended, its immense pent-up energy had to go somewhere. That energy flooded the universe, reheating it into a roaring ocean of particles and radiation, setting the stage for the next great act, the creation of the first stable matter. This primordial energy released by inflation's end did not simply vanish. It forged a new reality, a universe so unimaginably hot and dense that the very building blocks of matter as we know them could not hold together. For the next several microseconds, the cosmos became a seething, opaque broth known as the Quark epoch. It was a realm of pure potential, a particle zoo operating under extreme conditions. Quarks, the fundamental constituents of protons and neutrons, along with their force-carrying particles called gluons, roamed freely in a chaotic state known as a Quark-Gluon Plasma. If you could somehow visit this era, you would not find a single atom, not even a proton. The thermal energy was so immense that any attempt for three quarks to bind together and form a proton was instantly torn apart by the next collision. It was a frenzied dance of creation and annihilation, where particles and their antimatter counterparts constantly flashed into existence only to destroy each other moments later. Yet within this chaos lay the most critical detail for our existence. For every billion annihilations between a matter particle and an antimatter particle, a single matter particle was left behind. This tiny asymmetry, a 1 in a billion preference for matter, is one of the universe's deepest mysteries, a process we call baryogenesis. Without that minuscule imbalance, every last quark would have found an antiquark, and the entire universe would have devolved into a featureless sea of light with no stars, no planets, and no us. This Quark-Gluon Plasma was the universe's first and most volatile particle party, but the cosmos was cooling rapidly. A dramatic phase change was approaching, one that would permanently lock these free-roaming quarks into the stable matter that builds our world. The frantic dance of free quarks could not last. As the cosmos cooled below 1 trillion degrees, a cosmic lock clicked into place. The strong nuclear force, which had been too weak to overcome the immense thermal energy, finally gained the upper hand. This was the dawn of the Hadron Epoch, the moment quarks lost their independence forever, captured into permanent alliances. Trios of quarks bound together, forming the first stable protons and neutrons. For the first time, the fundamental building blocks of atomic nuclei existed as distinct, enduring entities. The universe was now filled with a thick, searing fog of these new particles, a plasma so dense that light was trapped, constantly bouncing between them. This era was marked by a final, catastrophic cleaning. The matter and antimatter that had flickered in and out of existence now met in a final, all-consuming embrace. Protons annihilated with antiprotons, electrons with positrons, in a universe-wide flash of gamma radiation. it was a cosmic reset of staggering proportions. Yet, because of that 1 in a billion asymmetry from the previous epoch, a tiny surplus of matter remained when the fire died down. Every proton and neutron in your body is a relic from that ancient inferno, the surviving ash of a near-total annihilation. The universe had successfully forged stable matter, but it was a world still utterly dominated by the blinding glare of radiation, a place where light called all the shots. This balance of power, however, was destined to be shattered. The blinding fire of the Great Annihilation began to fade, leaving behind a universe still searingly hot, but now dominated by a new cast of characters. This was the reign of the lightweights, the Lepton epoch. Electrons and their antimatter twins, positrons, filled the cosmos in staggering numbers. The energy was still so intense that pure light, in the form of gamma-ray photons, could spontaneously transform into a pair of these particles, a particle and an antiparticle born from a flicker of energy. An instant later, they would find each other and vanish back into the light from which they came. The universe was a churning, dynamic sea of creation and destruction, teeming with light and these lightweight, fundamental particles. It was during this chaotic dance that one of the most elusive particles in existence decided to leave the party. Neutrinos, ghostly particles that barely interact with anything, found themselves suddenly free. As the cosmos expanded and cooled, it became transparent to them. Billions of years before light would gain its freedom, these neutrinos simply stopped interacting with the rest of the cosmic soup and began streaming unimpeded through the rapidly growing void. This event, known as neutrino decoupling, created a cosmic relic that still washes through you every second, a faint whisper from the universe's fiery youth called the cosmic neutrino background. Meanwhile, the final, decisive battle between electrons and positrons was reaching its climax. In a final, universe-wide blaze, these matter-antimatter pairs sought each other out and annihilated. But thanks to that same ancient 1 in a billion asymmetry that saved the protons, a tiny surplus of electrons remained. This was not a random accident. The number of surviving electrons was perfectly tuned to match the number of surviving protons, ensuring the universe would be electrically neutral. This balance was absolutely critical. Without it, the powerful force of electrical repulsion would have prevented protons from ever capturing electrons, making the formation of atoms, and therefore all chemistry and life, utterly impossible. The stage was now set, the conditions perfect. The universe had simplified itself from a chaotic zoo of particles into a hot, dense, and neutral fog of atomic nuclei and free electrons, patiently waiting for the moment it would finally step out of the shadows and into the light. For nearly 400,000 years, the universe was a brilliant, impenetrable fog. Light itself was a prisoner. Photons, the particles of light and radiation, could not travel more than a minuscule distance before bouncing off a free electron in a frantic, endless game of cosmic pinball. This was the photon epoch, an age defined by its very opacity. If you could witness it, you would see nothing but a uniform, blinding glow in every direction, a searing plasma where atomic nuclei and electrons swirled in a hot, dense soup. Yet within this luminous prison, the first seeds of chemistry were being sown. During its first few minutes, the universe had acted as a perfect fusion reactor. Protons and single neutrons collided and fused, first forming deuterium, a heavy form of hydrogen. These deuterium nuclei then rapidly combined to form the nuclei of helium, with trace amounts of lithium also emerging. This brief, explosive burst of nucleosynthesis set the cosmic ledger for the next billion years. The precise ratios it produced, a universe composed of about 75% hydrogen and 25% helium by mass, became one of the most stunning confirmations of the Big Bang theory. Every star that would ever form would inherit this primordial composition, a fundamental legacy from the universe's first moments, but the cosmos was still too energetic for the next critical step. The free electrons acted as a constant disruptive force, preventing these new nuclei from capturing electrons to become stable, neutral atoms. The universe was poised, waiting for a single, transformative event. As expansion continued, the cosmic plasma cooled past a critical threshold, setting the stage for a sudden transparency that would forever change the nature of reality. The universe held its breath for nearly 400,000 years, a brilliant, opaque prison of light and plasma. Then, in a single, transformative moment, everything changed. The cosmos had finally cooled to a point where the chaotic dance of particles could no longer be sustained. This event, known as recombination, was not a recombination of things that had been together before, but rather the very first union. For the first time, atomic nuclei, primarily hydrogen and helium, managed to capture those free-roaming electrons, pulling them into stable orbits to form the first complete neutral atoms. It was a cosmic marriage that altered the fabric of reality itself. The effect was instantaneous and dramatic. With electrons now bound securely within atoms, the endless game of photon pinball came to an abrupt halt. The fog lifted. The universe, for the very first time, became transparent. What was the immediate consequence of this sudden clarity? The photons that had been trapped for eons were suddenly set free. This was the universe's first true flash of light, a brilliant burst of illumination streaming in every direction at once. That initial flash of freedom is still traveling today, though you cannot see it with your eyes. Over the ensuing billions of years, the relentless expansion of space has stretched those primordial photons from visible light into the microwave part of the spectrum. We detect this ancient echo as a nearly uniform glow that fills the entire sky, the cosmic microwave background radiation. Its discovery in the mid-1960s was a stunning accident, a persistent hiss in a radio antenna that turned out to be the cooled remnant of the universe's fiery birth, the most powerful evidence we have for the Big Bang. But this cosmic snapshot holds an even deeper secret. Embedded within its near-perfect uniformity are tiny, whisper-quiet variations in temperature, minute ripples that represent slightly denser patches of the early universe. These are the gravitational seeds, the quantum wrinkles from the inflationary epoch stretched to cosmic proportions, that would one day become the galaxies and vast cosmic voids we see today. This moment of transparency was the universe's ultimate dawn, the end of its searing infancy and the beginning of a profound new chapter. With light now traveling freely across an ever-expanding void, the cosmos plunged into its next great phase, a deep and silent darkness that would last for millions of years. That brilliant cosmic dawn faded into a profound and lasting silence. For the next several 100 million years, the universe plunged into an era of absolute darkness known simply as the Dark Ages. The afterglow from recombination had stretched into faint, invisible radio waves, leaving no stars to pierce the void and no galaxies to dot the expanse. The cosmos became a vast, lightless sea of neutral hydrogen gas, a simple and quiet realm holding its breath. But this was not an empty silence. It was a silence of immense potential, a cosmic deep breath before a storm of creation. Within this pervasive darkness, the invisible architecture of dark matter was already at work. Its gravitational pull, focused on the tiny density ripples left over from inflation, began slowly, patiently gathering that primordial hydrogen. These slight overdensities acted as gravitational seeds, pulling in more and more gas over eons, growing ever so slowly in the chill of expanding space. What did the universe look like during this long night? If you could witness it, you would see only an unbroken, inky blackness in every direction, a perfect void. Yet, beneath that featureless surface, the first grand structures were slowly taking shape, vast webs of gas condensing in the dark. This was the universe's crucial period of gestation, a time when it transformed from a smooth, uniform fog into a tapestry of potential. All the while, the hydrogen gas cooled and condensed, its potential energy mounting, waiting for a single, catastrophic spark. That spark was coming. The gathering silence of the Dark Ages was the calm before a revolution that would shatter the cosmic quiet forever and ignite the first fires in the void. The deep cosmic silence was finally broken by a single, catastrophic spark. In the densest regions of gas that had gathered during the long Dark Ages, gravity achieved its ultimate victory, crushing hydrogen clouds until the pressure and heat at their cores became unbearable. The universe witnessed the birth of its very first star. This moment, known as cosmic dawn, was not a gentle sunrise but a sudden, violent ignition that set the void ablaze. These first stellar pioneers, called population 3 stars, were unlike anything that exists today. They were colossal behemoths, hundreds of times more massive than our own sun, and they were pure, composed only of the primordial hydrogen and helium forged in the Big Bang. Their nuclear furnaces ignited with a ferocity the cosmos had never known, flooding the universe for the first time with the brilliant, piercing light of true starlight. This new light did more than just illuminate the darkness. It fundamentally changed the nature of space itself. The intense ultraviolet radiation pouring from these massive stars was so powerful that it began to strip electrons from the neutral hydrogen atoms that filled the vast expanses between them. This process, called reionization, slowly burned away the cosmic fog, making the intergalactic medium transparent once again to specific wavelengths of light and clearing the channels for light to travel across vast distances. But the true, lasting legacy of these first stars was forged in their hearts. For millions of years, their immense cores acted as the universe's first and most powerful factories. Through the relentless process of nuclear fusion, they accomplished what the Big Bang could not. They cooked the first heavy elements into existence. Within these stellar forges, simple hydrogen and helium were fused into the building blocks of future complexity: carbon, oxygen, and even iron. The lives of these giants were spectacular but brief. After only a few million years, they exhausted their fuel and met their end in titanic supernova explosions, cataclysmic events that outshone entire galaxies. In their violent deaths, they performed their most crucial duty. They blasted these newly forged heavy elements out into the cosmos, seeding the primordial gas with the ingredients for rocks, for water, and ultimately for life. The universe was no longer a primitive realm of simple elements. It had begun its great chemical evolution, and the stage was now set for a new generation of stars to rise from this enriched cosmic ash. These stellar explosions were the construction crews of the cosmos, scattering the heavy elements that would become the bricks and mortar for everything to come. This enriched debris did not simply drift aimlessly. It was drawn into vast, swirling reservoirs of dark matter, the invisible skeletons upon which the first galaxies would be built. Small proto-galactic clumps began to merge, their mutual gravitational attraction pulling them into violent, beautiful dances. Over hundreds of millions of years, these chaotic mergers assembled the majestic spirals and ellipticals that now dot the void. This era of galaxy formation was the universe's great period of urbanization, transforming a scattered population of stars into vast, organized cosmic cities. At the heart of this frenzy, a new and mysterious class of object was taking root: Supermassive black holes with masses millions or even billions of times that of our Sun likely formed in the centers of these nascent galaxies. Their growth became intimately intertwined with the galaxy's own story, a feedback loop of accretion and incredible energy output that could either spur on star formation or quench it entirely. What did a young galaxy look like in this violent time? It would have been a far more chaotic and brilliant place than the Milky Way today, with frequent collisions triggering intense bursts of new stars and a central, bright quasar powered by the ravenous black hole feeding on in falling gas. Within these newly structured islands, stability began to emerge. Further generations of stars were born from gas clouds now enriched with carbon, oxygen, and iron. This was a pivotal change. It meant that when these new stars formed, they could be surrounded by disks of dust and rock that could coalesce into the first rocky planets. The universe was no longer a formless expanse. It had become a structured, hierarchical cosmos of defined systems. This organization was not just for show, it was absolutely crucial. By gathering stars into stable, rotating islands, galaxies created safe harbors where suns could burn for billions of years, and around them, worlds with the right ingredients for complexity could quietly form, setting the stage for the next improbable step. Our own cosmic neighborhood was born from a specific cloud of gas and dust, a place already rich with the history of the galaxy. This cloud, a cold and dark giant molecular cloud, had drifted for eons, its composition a testament to stellar lives long ended. It was seeded with the heavy elements from countless supernova explosions, each one contributing a share of the carbon, oxygen, and iron that would one day become our world. Then something disturbed its quiet equilibrium. A shock wave, likely from the violent death of a massive star not far away, rippled through this cloud, compressing pockets of gas just enough for gravity to take over. The cloud began to collapse, a slow and inexorable fall inward that would define everything we know. At the center of this swirling chaos, a dense, hot protostar began to form, gathering more and more mass until the pressure at its core ignited the sustained nuclear fusion of our Sun. The leftover material, a flattened disk of gas and dust swirling around this new star, became a construction zone. Within this disk, dust grains collided and stuck together, forming pebbles, then rocks, then planetesimals in a frantic game of cosmic accumulation. The result was our solar system, a family of planets each finding its place. The inner, rocky worlds like Earth formed from the dust and metal that could withstand the young sun's heat, while the outer giants gathered vast atmospheres of hydrogen and helium. This local story has the most profound cosmic roots. Every atom of iron that carries oxygen in your blood, every atom of calcium that strengthens your bones, was forged in the heart of a star that lived and died long before our Sun was even a glimmer. We are literally made from stardust, the recycled remains of ancient stellar furnaces. Earth itself coalesced in a particularly fortunate orbital zone, a region where temperatures were just right for water to exist as a liquid. This was the ultimate Goldilocks condition, a stable, rocky planet with the right ingredients and the right location. On this newly formed world, still cooling from its violent birth, the stage was now set for the most mysterious transition of all, the leap from a lifeless geochemical world to one teeming with biology. That transition from a lifeless world to a living one remains one of nature's best-kept secrets. On the early Earth, a remarkable alchemy took place, where non-living chemistry somehow crossed a threshold and became biology. The first self-replicating molecules appeared, launching an evolutionary journey that would, after billions of years, produce a species with a unique gift, the ability to look back at the cosmos and ask how it came to be. This marks the 13th epoch, the Anthropic epoch, the moment the universe woke up and became conscious of itself. We are that universe looking back at itself. This self-awareness forces us to confront one of the most profound mysteries in all of science, the apparent fine-tuning of the cosmos. Why do the fundamental constants seem so perfectly set for life? The strength of gravity, the force binding atomic nuclei, the mass of an electron, if any of these were altered by even a tiny fraction, the universe would be sterile. Stars would not form, complex atoms would never exist, and life would be an impossibility. This observation is known as the Anthropic principle, the idea that the universe we observe must be compatible with the existence of observers. But what does this fine-tuning mean? One compelling suggestion is that our universe is just one of a vast multiverse, an immense collection of cosmic domains, each with its own random set of physical laws. In this sea of possibilities, we simply find ourselves in one of the rare habitable pockets where the numbers lined up just right. Alternatively, could there be a deeper, more fundamental reason for this cosmic harmony? A unified theory that necessarily produces a life-friendly reality. The rise of intelligence represents a new and powerful phase in cosmic history. For billions of years, the universe simply was. It created stars and galaxies through mindless physical processes. But with the emergence of conscious minds, it gained the capacity to understand its own origins, to trace its history back to the first instant of time, and to contemplate its ultimate fate. Through science and reason, the cosmos is now exploring its own story, a story that is still being written, with our own choices and discoveries becoming a small but meaningful part of the narrative. This brilliant era of starlight and life is not our universe's permanent state, but merely a fleeting, vibrant phase. We now exist within what astronomers call the Stelliferous Era, a time dominated by shining stars. Yet every star is a temporary furnace burning through a finite supply of fuel. Over trillions of years, the great reservoirs of interstellar gas, the raw material for new stars, will be gradually depleted. The grand stellar nurseries will fall silent, and the last generation of stars will ignite. These final suns will be small, dim red dwarfs, hoarding their fuel for stretches of time so long they dwarf the current age of the universe. But even their endurance has a limit. One by one, they too will exhaust their hydrogen, cooling into dark, inert spheres of helium. The last star in the cosmos will eventually flicker and die, and with its passing, the Stelliferous Era will draw to a close. The universe will not vanish, but it will transform into something almost unrecognizable. The stage will be left to the stellar remnants, the ghostly remains of stars long departed. Fading white dwarfs, ultra-dense neutron stars, and solitary black holes will become the primary inhabitants of this new, dark age. The galaxies they inhabit will also face a slow demise. Through complex gravitational interactions over almost unimaginable eons, stars will be flung out into the intergalactic void, their home systems gradually evaporating into a sparse haze of isolated objects. At the center of each galaxy, the supermassive black hole will remain, growing slowly by consuming the occasional stray star or gas cloud, a patient monarch in a darkening kingdom. This cosmic decline is not a violent end, but a slow, quiet fading, a descent into cold and darkness governed by the same immutable laws of thermodynamics that allowed for the rise of complexity in the first place. It is a humbling perspective, revealing that the vibrant cosmic activity we see today is a brilliant but temporary chapter in a much longer and quieter story. And yet, even in this era of fading light, the universe holds the potential for one last, strange form of activity. The stellar era's final embers cool into darkness, leaving behind a ghostly new reality. We now enter the Degenerate Era, a phase defined by the fading remnants of stars. The universe is populated by the incredible densities of white dwarfs, neutron stars, and solitary black holes, all coasting on residual heat in a cosmos that is expanding into a profound and lasting chill. The faint, residual warmth from these objects represents the last organized energy in the universe, a slowly fading memory of its vibrant past. During this almost endless epoch, the very fabric of matter itself may face its ultimate dissolution. The proton, the stable, positively charged particle at the heart of every atom, might not be eternal. Over timescales so vast they defy comprehension, some theories suggest that protons could spontaneously decay, dissolving the fundamental bedrock of all normal matter. If this occurs, every white dwarf and neutron star would gradually evaporate, their substance leaking away into the void. This would leave black holes as the sole large-scale structures, ushering in the next and nearly final chapter. This is the black hole era. For an incomprehensible length of time, these gravitational titans will rule a dark and nearly empty cosmos. They are not static, however. Through a remarkable quantum process predicted by Stephen Hawking, these cosmic traps are not perfectly black. They slowly, ever so slowly, leak radiation, losing minuscule amounts of mass over eons. A solitary black hole, isolated in the void, emits a faint whisper of particles, a process known as Hawking radiation. As a black hole loses mass, its evaporation rate accelerates. What begins as a barely perceptible trickle becomes a final, brilliant flash. In the very last instant of its existence, a black hole would release all of its remaining energy in a sudden, final burst of light and particles. One by one, across the dark expanse, each black hole would meet this fate, from the stellar mass ones to the supermassive giants at the centers of long-vanished galaxies. The last great black hole in the universe will eventually vanish in a similar, silent flash, marking the end of an era. What remains is the final possible state, the dark era. The universe becomes a vast, cold, and nearly featureless void. It is a cosmos of extreme simplicity, filled only with a desperately thin sea of fundamental particles like photons, neutrinos, and electrons, all continuing to spread apart as space itself expands forever. The temperature approaches absolute zero, the point where all meaningful thermal energy is gone. This is the ultimate expression of what we call the heat death, not a fiery explosion but the final, permanent equilibrium. All energy is evenly distributed, all gradients have been flattened, and the universe has achieved a state of maximum entropy where no further work can be done, and no new structures can form. This is the final, direct consequence of the initial conditions set in the first moments of the Big Bang. The universe that began in a state of ultra-hot, ultra-dense complexity ends its story in a state of ultra-cold, ultra-diffuse simplicity. The cosmic story has come full circle, from a single point of infinite potential to an endless, quiet expanse, a final, profound silence that echoes its first moment. This cosmic fine-tuning is not a minor detail but a fundamental feature of reality. The universe operates on a set of numbers so precise they seem chosen. Consider the strength of the force that binds atomic nuclei, the strong nuclear force. If it were just 2% stronger, the universe would consist entirely of diprotons, simple 2-proton nuclei, and no hydrogen would exist. Without hydrogen, there would be no water, no stars like our sun, and no long-lasting stellar fuel. Conversely, if this force were slightly weaker, protons would not stick together at all, and no complex atomic nuclei could ever form. The universe would be a boring soup of solitary hydrogen atoms, incapable of building anything. The mass of the electron is another perfectly set dial. If it were even a little different, the chemistry that forms molecules would break down, preventing the stable bonds that create DNA and proteins. The very fabric of reality appears stitched together with these golden ratios. How can we explain such a breathtaking series of coincidences? One compelling answer lies in the concept of a multiverse. Imagine a vast cosmic ocean where countless universes bubble into existence, each with its own random set of physical laws and constants. In this infinite ensemble, most universes would be stillborn or sterile, incapable of supporting any complexity. We, of course, find ourselves in one of the rare habitable pockets where all the numbers lined up just right. Our existence is then not a miracle, but a selection effect. We are here because this is one of the few places that could possibly support observers. This idea, while speculative, offers a naturalistic explanation for the apparent fine-tuning. Alternatively, could there be a single, elegant theory of everything that logically requires the constants to have the values they do? Perhaps the laws we see are not arbitrary, but the only possible outcome of a deeper, unified principle. This fine-tuning is the golden thread connecting every epoch we have explored. From the initial split of the fundamental forces that set the constants, to the inflationary expansion that smoothed the cosmos, to the precise nuclear reactions in the first stars that forged carbon, each critical juncture relied on these perfectly balanced values. It suggests that the potential for life was written into the cosmic code from the very first instant, a silent promise woven into the fabric of space-time that would only be fulfilled billions of years later on a small, rocky world. This grand cosmic narrative, woven across 15 pivotal epochs, reveals a universe of profound connection and breathtaking scale. From a fleeting quantum fluctuation in the first instant to the emergence of conscious life, we have traced a chain of causality that binds the fate of galaxies to our own existence. The precise way gravity separated during the Planck epoch determined how those first density ripples would form, which in turn orchestrated the gravitational collapse of gas that became the majestic spirals we observe today. Every star, every planet, and every living thing is a direct product of this unbroken chain of events, a legacy written into the fundamental laws of nature at the very beginning. Understanding this story transforms our perspective. We are not just passive observers living on a random rock in space. We are the universe becoming aware of itself, a collection of atoms forged in stellar furnaces, now capable of contemplating the very cosmic processes that created us. This knowledge is a profound form of empowerment, a reminder that we are an active and integral part of this ongoing evolutionary saga. The same forces that sculpted galaxies and ignited stars also assembled the complex chemistry that allows you to watch this video and wonder about it all. This journey through cosmic history is ultimately your own origin story. If this exploration of our shared beginnings resonated with you, consider subscribing for more deep dives into the universe's greatest mysteries. We would love to hear which of these 15 epochs you find most fascinating, so please share your thoughts in the comments below. The story of the cosmos is far from over, and we are all here together to read its next chapter.